Slovanov's work is comparable to Einstein. He's probably the most underrated computer scientist of all time. And I think I was thinking on the train here that probably the only other computer scientist I can compare Solomonov to is Turing, because he had exactly the same attitude. He made this really simple, extremely simple model of computation, right? It's extremely simple, but it still works. It's universal. It explains all computation. And Solomonov's work on probability theory is likewise. And this great formula, well, don't mind that it's deceptively simple. It explains a lot, as we all know. And this guy here is the algorithmic probability of bit string X relative to a universal computer U. And well, I suppose you all know this, right? You're all familiar with it, so there's not much need to expand. And the HUX here is algorithmic complexity, also known as Kolmogorov complexity, which is the length of the minimal program that generates its blah-blah. All right, and now let me give you an example of the application. Operator induction is inferring conditional probability density functions, and it works for any such computable function. And we feed the system with question-answer pairs, and then the system is able to infer answers from questions. It's a question-answer machine. Okay, now we're getting to the meat. Here I defined pi star, which is supposed to be the optimal program that simulates a given conditional probability density function. So as applied to operator induction. Well, operator induction is pretty general. It's what I would call an AI complete problem. Yeah, so you can reduce a lot of AI problems, hard AI problems, to operator induction. That's what I'm trying to say. And therefore it makes sense to think a bit about this formalization. And so this is a program that simulates a given stochastic source mu. Mu is a computable conditional probability density function. PDF, I will abbreviate further on. And it's the minimal such program that precisely, accurately simulates mu here. Well, conceptual jump size is predicts the running time of a complete, the optimal induction. So it's just a limit, but even if you use Levin search, which is very expensive, 2 times conceptual jump size is the upper bound. So it's not going to cost you more than that. And here we are very interested in bounds in this paper. So I thought I would define it for stochastic sources as well. So what this notation means here is, it's a shorthand, I know, and but it makes some sense. The conceptual jump size of stochastic source mu is the time it takes for the optimal program, the shortest program that simulates mu, divided by its a priori probability. And this is, of course, relative to a universal computer U. Well, there are a lot of such formulas. I don't know if the presentation is going to be finished if I explain them all in detail like this, but I'm going to try my best. So, and we can also define a stochastic version of algorithmic complexity. And then you have this, the time bound that you see below. Oh, there was a pointer, where is it?
It was next to the red little thing.
Ah, okay, thank you. All right, so this guy, yeah, thank you, Arthur. And yeah, so I mean here is that it depends on the, of course, algorithmic complexity of mu. I'm not going to elaborate. You should read the paper. Okay. So, well, how do we measure induction? I'm going to try to keep it as simple as possible, but I'll probably fail. I'm not as smart as I can, of course. So, so you should bear with me, and if you have questions, please do ask. Okay, so, well, if you use the big O notation, so that's what we're going to get. It's exponential, right? And it increases exponentially with increasing complexity of mu. And what is this? This is this is a stochastic logical depth. And of logical depth was defined by Bennett as the time it takes for the minimal program to complete. So this just fits the definition we just made in the previous slide. So this is a stochastic kind of logical depth relative to U. But we don't really have to write U everywhere. But I was just being pedantic. We have just one universal computer here, okay? Not too many. And okay, and so now we have some kind of relationship between the running time upper bound and stochastic logical depth, just like this. Okay, that looks a bit interesting, but it's not too interesting. It's going to get a little more interesting. And this is a really trivial. It's just straightforward. I have 5 minutes? Wasn't it total 15 minutes? 15? Okay, that's great. Wow. So let me get to the theorems then. So this says the running time bound is less than the expected time to simulate stochastic source mu. And we have a graphical model of computation. We use a bipartite graph to model the causal events that constitute the computation. And so those are events, and we have outputs, vertices, and some input vertices. It's really easy, you can see it in the paper. So we can generalize the philosophical definition I made in the first paper and calculate them over this graphical model. So we have space-time volume complexity, energy complexity, and the space complexity, which is the maximum volume of a time slice of computation, right? And then we can define a logical depth in terms of volume and energy, and then this gives us conceptual jump volume and conceptual jump energy. So you can guess what it is. It's straightforward. And then we have an energy bound. The energy it will take to simulate the stochastic source will be related to the will be related to the volume and space complexity, And well, if you use Einstein's formula, assuming that it's at rest, then it's the addition of a logical volume depth and space complexity here. So we get this expression, and we define this conceptual jump energy here. And well, the gist of the paper is it gives us a boundary conditional induction. So this means the energy required to simulate mu is linearly proportional to the logical volume of computation and the maximum memory space, physical space required by the computation, and exponentially, and this is multiplied by the exponent of the algorithmic complexity. And what does this mean? Well, it means energy is important. So we can define an energy prior, which is just like the speed prior, but instead of speed or time, we use energy. So this is a new idea, relatively. And then we can apply this stuff. Schmidt-Huber first applied this, and he obtained a bound like this. So in this universe, all right, in this universe, you cannot infer correctly and more than 397.6 bits. If there's a stochastic source that exceeds this complexity in number of bits, you are not going to be able to infer it, assuming that the logical volume is 1, which is 1 meter in this case. So well, that's it. I know this was a little a little cryptic, but this was the best I could do. And I bet you have questions. You might have questions, so you can email to me at examination@gmail.com, and I'd like to take some questions, immediate questions, if you have any now.
There will be a panel discussion.
All right. Thank you.
Let's send